Hi guys, for today's video, I'm gonna discuss about the Delta-Wye transformer connection, voltage and current relationship, and its phasor diagram with corresponding angle. So let's start.
So I have here the three-phase transformer diagram with two windings. We'll assume that the winding on the left is the primary side, the HV side or the source side, and the winding on the right is the secondary side or the low voltage side or the loaded side. So we'll draw our polarity marks to indicate the polarity side of the winding, and we also indicate the magnetic coupling with two parallel lines. And lastly, we assume that the primary line-to-line voltage is 4160 volts, while the secondary line-to-line voltage is 480 volts. So we assign the capital letters to the primary winding and the lowercase to the secondary winding. So here is lowercase and secondary. So to make the three-phase transformer, we simply add winding B and C. So since we're starting a Delta-Wye transformer connection, let's start by connecting our secondary winding in Y. So we're going to connect the winding A, winding B, and winding C together. So, and for the sake of simplicity, we're going to ground the neutral wire. So this is the wire grounded transformer connection. This wire grounded transformer connection has a various characteristics than Y ungrounded transformer connection. So in the primary side, we are going to connect earn delta. Since this is a Delta-Wye connection, connect the primary winding like this. So we all understand that the phase voltage or voltage measure across the transformer windings. So let's illustrate primary phase A voltage, which is measured across the polarity side of winding A and the non-polarity side of winding A. Similarly, we illustrate the primary phase B voltage and the primary phase C voltage. On the secondary side, we illustrate the secondary phase voltage, secondary phase A voltage and secondary phase B voltage and secondary phase C voltage. So line-to-line voltage, however, are measured across two lines. The most common line-to-line voltage are measured across line A to line B. The most common line-to-line voltage are measured across line A to line B. Line A to line B. And from line B to line C, and from line C to line A. So on primary side, where our transformer is connected in delta, we should expect the line-to-line voltage line across line A and line B is equal our phase A voltage. So suppose we label point A, the point A, and point B as the point of measurement. Point A is the same as the line as polarity side of winding A. So the point B is the same to the point of the line as non-polarity side of winding A. Polarity side of winding A. So if we measure across point A and point B, we actually measuring across the polarity side of winding A and the non-polarity side of winding A. Similarly, the line-to-line voltage across line B and line C is equal to phase A voltage, and line-to-line voltage of the line-to-line voltage across line C and line A is equal to phase C voltage. So for a delta connected transformer, we should expect the voltage across two lines to equal the voltage across a single winding, or in other words, the line-to-line voltage equals the phase voltage. So on the secondary side, where our transformer is connected in Y, the most common line-to-line measurements are across the line A and line B, across line B to line C, and lastly across line C and line A. So the line-to-line voltage measurements across line A and line B is equal to phase voltage A minus phase voltage B. For a Y-connected transformer, if we look at the magnitudes alone, we should expect the line-to-line voltage is equal to square root of 3 times the phase times phase voltage. So there is certainly going to be some phase shifts involved between the two voltages. So what's the line-to-line voltage between line B and line C? So it's phase B voltage. So it's phase B voltage minus phase C voltage, which is equal to the square root of 3 times the magnitude of phase B voltage, which is also equal to the square root of 3 times the magnitude of phase C voltage, or simply the square root of 3 times the magnitude of any phase voltage. And of course, we're assuming that we have a balanced set of voltages. So if we took a super duper voltmeter and measured across line A and line B on the primary side of our transformer, we should expect 160 volts. This is our line-to-line voltage. that we assume. So similarly, the voltage across line B and line C is equal to 4160 volts. And also the line to line voltage across line C and line A, we should also equal 4160 volts. Both phase B and C should also equal to 4160. And also the both B and C should also equal to 416 volts. On the secondary side, where our transformer is connected in Y, if we measure the voltage across line A and line B, we should expect that 480 volts for the line-to-line voltage. So we measured across the polarity side of winding A and non-polarity side of winding A. So we would have to derive that from line-to-line voltage. For Y connected transformer, the line-to-line voltage across line A and line B. So line A and line B is equal to phase A voltage minus phase B voltage, which is equal to the square root of 3 times any phase voltage. Since we already know that our line-to-line voltage is 480 volts, so we simply solve for the phase voltage by dividing 480 volts. 480 is equals to square root of 3 phase voltage. So we simply solve for the phase voltage by dividing 480 volts. So 480 volts divided by the square root of 3 by the square root of 3. So which gives us approximately 277 volts. So phase A voltage is equal to 277 volts. Similarly, phase B voltage is 277 volts, and the phase C voltage is equals to 277 volts. And line-to-line voltage across line B and line C is equals to 480 volts, and line-to-line voltage across line C and line A is equals to 480 volts. So on the secondary side of transformer, where our transformer is connected in Y with a neutral grounded, we understand that line current or line-to-line current, as I like to call it, is current that flows through the lines of or conductors. Since we're assumed that the secondary side is our load side, we understand that the line current will flow through our lines to our load. So line-to-line current A will flow through line A, and line-to-line current B will flow through line B, and the line-to-line current C will flow through line C, and they will all feed our load. So our transformer is connected in delta on the primary side or the source side. So the line-to-line current A, the line-to-line current A will flow through line A. Similarly, line-to-line current B flow through line B, and line-to-line current C will flow through line C respectively. On the secondary side, where our transformer is connected in Y, we should expect that phase A current to come from winding A and flow to our load. Similarly, phase B current comes from winding B and flows to our load, and phase C current comes from winding C and flows to our load. So since we know that the secondary phase A current flows out of the dot on the secondary side, that simply means that the primary phase A current must flow into the dot of the primary side. So primary phase A current will flow into the dot, and secondary phase A current will flow out of the dot. So similarly, the phase B current, must flow into the dot on the primary side to make secondary phase B current flow out of the dot on the secondary side. And lastly, phase C current must flow into the dot on the primary side to make secondary phase C current flow out of the dot on the secondary side. We understand that the primary phase A, primary phase B, and C current flow through the polarity side of the primary windings, and the secondary phase A, B, and C currents flow out of the polarity side of the secondary winding. So for a Y-connected transformer, it's easy to see that phase currents line to line A currents are both equal. So for the delta connected transformer, we don't have the same one-to-one relationship between line currents and phase current. So we will call the node A1 that connects the polarity side of winding A the non-polarity side of winding C. Then we will call the node B1 that connects the polarity side of winding B and the non-polarity side of winding A. So lastly, we call node C1 the nodes that connects the polarity side of winding C and the non-polarity side of winding B. So we know that the primary phase A current flow into the polarity side of winding A and out of polarity side of winding winding A, which means that the current that flows out of the node A is phase current. So since the non-polarity side of winding A is connected to the polarity side of winding B, the current goes into the node B1 is the same phase A current. So let's move to the phase B current. That primary B current must flow into the polarity side of winding B and out of non-polarity side of winding B, which means that the current that flows out of node B1 is phase B current. So since the non-polarity side of winding B is connected to the polarity side of winding C, the current that goes into the node C1 is the same phase A current. And lastly, the phase C current must flow into the polarity side of winding C and out of non-polarity side of winding C, which means that the current that comes out of the node of C1 is phase current C. So since the non-polarity side of winding C is connected to the polarity side of winding A, the current that goes out of node E1 is the same phase as current C. So now we've illustrated the phase current. Let's quickly label our current. So our line current. So line to line current. So line to line current A will flow line A into the bushing of winding A and finally into node A1. So similarly, line to line current B will flow through line B into the bushing of winding B into the node B1. And lastly, line to line current C will flow through line C into the bushing of winding C and finally into the node C1. So when we apply the KCL or Kirchhoff's current law, we can simply express this relationship as in node A1. So line current A plus current C is equals to the current A. The currents that are flowing into node E1 is equal to the current that are flowing out of node E1, or simply line current A plus phase current C is equal to phase current A. So similarly, for node B1 line current B plus phase current A is equal to the phase current B, and phase current A are flowing into node B1, but phase current B is flowing out of node B1. So lastly for node B1 line current, first node B1 line current C plus phase current B is equal to phase current C line current C, and phase current B are flowing out in So now we're going to evaluate this particular equation and look from a phasor diagrams prospectively. So line current A is equals to phase current A minus phase current C. Similarly, the line LL current B is equals to phase current B minus phase current A. And lastly, line current C is equals to phase current C minus phase current B. So now that we've written our equation like this. So our phase values are the currents that are flowing through our windings. So we're going to define what our phase A occurring is going to define phase B and phase B current and phase C current. So we're going to define these currents and create a balance system. So let's say that our phase current A is equals to 1000 amps at 0 degree. Phase current B is equals to 1000 amperes at 240 degree. And lastly, phase current C is equals to 1000 amps at 120 degree. So now we're doing a nodal analysis on node A1, and we're actually trying to solve with a phasor diagram in this particular equation. So what this line is the current equals when we subtract our phase current A minus phase current C. So let's draw a phasor diagram. So this is our phasor diagram. So this line here at the 0 degree mark is our reference line. So this phasor here, this phasor that's going through our reference line, which is which is at 0 degree. This is a phase current A, and we're saying is that from this origin point here is to the point, this here is a 1000 amperes. So and the angle is at 0 degrees, which is the same direction as a reference line. This phasor here is our phase B. Here is our phasor B current, and from this origin here to here is our 1000 amps, and the angle which is 140 degrees of what we define that angle is from the reference here, from the reference line going a counter, going in the counterclockwise direction until we've gone our 240 degrees. And lastly, this phasor here is our phase C current. So phase C current from origin to the end, or to the end of the tip here is a 1000 amps. 1000 amps. In the angle from the reference here, line going to counterclockwise here is 120 degrees to get to this phasor. So we're saying that this angle here, right here, is 120 degrees, and we're saying that this angle here is 240 degrees. So if this is our phase current A in positive side, so while the opposite would be the negative side, so our line to line voltage of winding A is equal to phase current A minus phase current C. So let's rotate this into 180 degrees and put this in current C here. Just so let's assume to find line to line voltage, so this is negative. This is our phase current. This is our phase current A, and so this is our phase current C. So the resulting vector will be here. So our resulting vector would be our line to line current A. So this is would be our line to line current A. So our second equation is line to line current B is equals to phase current B minus phase current A. So since this is our positive A, the opposite would be our negative. So let's put the negative phase current A here. So this is our negative phase current A. So the resulting vector would be line to line voltage B. Line to line voltage B. So in getting line to line current C, we equate this in phase current C minus phase current B. So this is our B, and we have the negative side. So let's rotate a 180 degrees and put the phase current B here, and its resulting vector would be our line to line voltage C. Line to line voltage C. Going back to our voltages, let's make a phasor analysis about the voltages. So this is our source side. This is our source side. So source side. it has a grounded wire. So let's connect this here to here. So this is our line A. So line here to here is our VJ8, and from here to here is our VGB, and this is our VGC. So in analyzing this, so we know that VAB is equals to phase voltage A. So our VAB here is VAB is equals to VGA minus VGB. So let's assume that our VGA is equal to 225 volts at 0 degree, while our VGB is equals to 225 volts at 240 degrees, while our VGC is equals to 225 volts at 120 degrees. So let's plot this on a graph. So this is our 0 degree. So we all have the VGA. So here, so this is our 0 degree. So this is our VGA, 225 volts. So we have the 240 here. This is our VGB 225 volts, and at 120 degree here is our VGC 225 volts. So we have equation here. We need to find getting our VAB. So in getting our VAB, we need to minus the VGA, subtract our VGA to VGB. So our VGA is here at 0 degree, and this is a negative sign of VGB. So since this is negative, we rotate this into 180 degrees. So our VGB here, so we need to rotate this into 180 degrees. So our VGB here is here, VGB. So the resulting vector would be our VAB. So we will relate VGA to VAB. So we would have to shift VGA by 30 degrees. In the 30 degrees in the counterclockwise direction, and we have to multiply it by square root of 3. So it lines up with VAB by Now we have to shift VGA to the 30 degrees counterclockwise direction and multiply it by square root of 3 VGA. Square root of 3, it would be overlaps VAB, which means that VAB is equals to square root of 3 VGA rotated at the 30 degrees. So similar with BBC, so we get the equation BBC. So BBC equals to VGB minus VGC, and also our BCA is equals to VGC minus VGA. So here is our VGB. To find the BBC, then we need to look our VGC. So this is our VGC. Since this is the positive side, so let's rotate it into 180 degrees. So 180 degrees. This is for VGC, and its resulting vector would be our VBC. So we shift this also by 30 degrees in counterclockwise direction. Same with BCA. Same with our BCA here. Same here with our BCA. If you get the BCA in the phasor diagram, we plot it. Take a look for VGC. So here VGC. This is our VGC, and this is our negative, and this is our negative VGA. So this is our VGA. So our negative is here. So rotate at 180 degrees. So our VGA will be here, VGA. So our resulting vector would be our VCA. So there are also 30 degrees counterclockwise direction. So this is voltage phasor diagram analysis, and that's all about a Delta-Wye transformer connection. Thank you.